and uploaded for distribution. Please use the text chat function in the Zoom window to submit questions anytime throughout the webinar. I'm Andrew Fung, Client Technology Advisor of Microsystems and Nanotechnology at CMC, and I'll be moderating the webinar today. Also presenting are Farouk Azizi from CMC and Marie-Josée Gour from 3IT at the Université de Sherbrooke. The webinar will cover an introduction to CMC Microsystems and specifically this silicon JFET platform, and then a tour of the process design kit. Marie-Josée will then present the fabrication process in more detail and some of the results of process control modules before going into a couple of example R&D applications. And then finally, I will give you some detail about how to participate in the lead user run, which is scheduled and coming up. So first, a quick introduction to CMC Microsystems and Canada's National Design Network. CMC is a Canadian national non-for-profit organization headquartered in Kingston, Ontario, with also offices in Ottawa and Winnipeg. Its mission is to enable and support research in micro-nano systems. And we do this by leveraging or delivering 5 key services: design tools or CAD tools, fabrication services, equipment services for characterization and test, training and support events, and fifthly, strategy and network management. The subject of today's presentation is specifically the introduction of a new platform technology. So let's begin just with an overview of the principle of operation. Shown on screen here is a conventional transverse junction field effect transistor, or JFET. It's formed by source and drain contacts that define a lateral conductive channel through the silicon. The conductivity of the channel is modulated by the depletion region at the PN junction, which is in turn controlled by gate electrodes. The novelty with this particular technology is that these JFETs are delivered with an open upper gate. And this allows the designer to integrate a functional material directly onto the semiconductor at that location. The functional material can act as the upper gate to modulate the channel conductivity. So this platform is useful for the study and optimization of novel hybrid material systems in silicon and the realization of some higher performance CMOS compatible detectors. A process design kit has been developed to enable you to design into this JFET process. And the following documents shown on the left and design tools are conveniently bundled into a single cloud environment. They include a user guide that explains the process and design rules, a layout template, and a design rule checking deck in a Tanner L-Edit environment, and also a reference design and a simulation package for a photovoltage FET using Synopsys Centaurus. Please do note that the PDK does not include licenses of L-Edit and Synopsys. The designer must order these tools separately, but they are offered in CMC's suite of CAD tools. Now, the flowchart to the right shows the activities that a designer would typically follow to prepare a layout for submission into a fab run using this process design kit. The design would then be submitted for fabrication at the laboratory at 3IT and ultimately delivered to the designer for integration of a soft material and experimentation in the designer's own facility or benchtop. Next, my colleague Farouk Azizi will demonstrate the cloud design environment. So over to you.
Hi, everyone. I will start with the product page and the information that are available in that page. I should make a note that this product page will be available shortly after our webinar. And we will be sending an email with the instructions how to access and find the link for this product page. The PDK is accessible through CNDN cloud, and you can access that PDK by clicking at Access PDK on the product page. It will ask you to log on to your CMC account, but here, since I have logged on to my account, then it just directly forwards me to the page that I can create an instance. And as you can see here, I already have an instance from before, but just for the sake of simplicity and presentation, I will delete this one and show you how to create a new instance. So you go to Create My Instance tab and find OpenGate JFET, which is here. Create your instance. Specify the time that you would like to use that instance, which is from 1 hour to 5 days. Let's say 1 hour here. Then you will be directed to this page, which is Manage My Instance. You connect. It will take approximately about 1 minute to be able to see the logon information to the instance that you requested. So it's just, can wait another 2 seconds. While this one is preparing, I would like to direct your attention to a document that that one will be available and will describe all the steps of accessing the process design kit. In that, which is, we call it Quick Start Guide, we explain what is included in the process design kit, which is a user guide describing the fabrication process, an application note for the reference design that we have for this project, a design layout in Tanner L-Edit, and simulation folders, which there are 2 for Centaurus, Synopsys Centaurus. Here in this section, you will see the system requirements for accessing the PDK, which again, at this point, it is only through CNDN cloud design environment. And for installing and licensing, we have a description of the CNDN cloud design environment. Once you click on this page, it will take you to a place that will explain and describe the cloud design environment that is offered by CMC. To access the PDK, the user requires to have a license for the 2 tools that I mentioned, Synopsys Centaurus and L-Edit, as my colleague also pointed out, along with the designer subscription. To access the PDK and fabricate a device, you will need access to those licenses plus prototyping subscription. And in the continuation of that document, you will see how to, the instructions to create that instance. But let's go back here. So once you have your instance created, you click on either one of these two environment, and the no machine is the one that I use a lot because it's easier to relate to. It's closer to Windows, and you follow don't update. Okay, so here at this point I have to okay, so I have to okay, so finally we are able to log on to our instance. So on the desktop of your instance, you see CAD launcher. Double click on the CAD launcher. You will be able to see two buttons, tools and kits. You go to the kits, select Open Gate JFET. And now you have access to the design environment, the layout design for Tanner, and the simulation from Centaurus, and the process design kit materials. So I will, for example, start with L-edit. To take a few minutes.
Just while we're waiting for this to run, I'll take the opportunity to remind those who've logged in the last few minutes. If you have any questions that arise during this, please use the chat function in Zoom to submit your questions, and we'll have a time at the end where we'll take some feedback from all of the community.
Okay, so let's go up. Yeah. So once we have our L-edit running, you will need to find the design file, which will define and create your design environment, which includes the design rules along with the dimensions that you can use for your device. So here, open. We need to go to CMC, kits. Design rules are described here along with and also here. Okay. By accident, I just run DRC on this. Obviously, there is no feature here to check. But now your design is set, and at this point, you can load the reference design. And the reference design is the same place as we found our layout design environment setup file. And as you can see here, there are cells that you could use for your own design. The design example that was used in the reference design is here. You can see some test structures. These test structures are added by the fabrication laboratory, and your design will look like this. When it does not have any of those test structures, you can apply this DRC, a tenor DRC, to this design. And here, we could now do the DRC and check the design layout dimensions. Okay, so the DRC results are listed here. Some of these errors that, or warnings that you have received are not based on the design rules. So for example, here, these error, it says about the, it talks about the angle that is 30 degrees, and an angle for the polygon that is 34, which is not one of our design rules. So you don't have to worry about this error, this one or this one. But here, I should mention that we have this error that it shows up here on DRC, but it should not have, because this is not an error. One of the design rules that tenor DRC is not capable of filtering out. We are in the process of switching to caliber DRC, and when this happens, we will not have this issue, which is showing up or having errors that are not, in fact, errors. And so that's for LEdit. And quickly, CentOS. CentOS, you will go to the same folder, CMC, kits, EIT, and you can choose any of these two designs and run the program. And from there, you can do your simulations. And the very last one is PDK material, which includes the two folders that we mentioned, reference design, user guide, and the layout design files, and a README file that will give you scripts to run LEdit and CentOS. Okay, going back here, it describes how to create the instance and how to do every single step. At the end, in appendix, I added an alternative way to run the tools that we just described. So that's pretty much it for me.
Okay. Thanks for that demonstration, Farouk. Next, I'll pass the screen share over to Marie-Josée Gour at Université de Sherbrooke. Screen share. So you've already seen an overview of the technology and then now a tour of the design environment. Next, Marie-Josée Gour will introduce the facilities at 3IT and detail the fabrication process there. So over to you.
All right, hello everyone. Thank you for joining us today. So before I get into the heat of the subject, for those of you who don't know us here at 3IT, I just wanted to take a few minutes to present 3IT, what we are or who we are, and what the goal is here. So in 2012, we have 49 researchers from various departments and faculties that joined us in one single building. Now, the intent of 3IT, which is Institut Interdisciplinaire d'Innovation Technologique, is to act as an incubator for scientific and technological innovation. So in doing so, when the researchers accept to come here, they take all their lab equipment and put it in a common infrastructure so that any 3IT user can actually use this infrastructure. As long as they have the proper credentials in terms of training in the lab and have proper training on the equipment per se. And this also applies to any external customer or someone, a startup or a company that actually wants to come and use our equipment or rent office space to use our facilities. So the 3IT is divided into 4 major labs. There's 3IT Nano, where we do micro and nano fabrication. There's 3IT Micro, which is where we do final die packaging and board prototyping. There's 3IT Mechano, which is a mechanical shop where we machine stuff. And finally, there's 3IT Studio, which is where we do the robots, and we have an environmental room where we have detectors in the walls, ceilings, floors, cameras everywhere, so that you can actually do more high-level system testing. So we try to address anything from the design concept all the way up to the full integration. Now, 3IT Nano per se has 4 major areas of research: 3D electronics, biomems, energy, and ethics. So last year we had about over 250 regular lab users coming into our facility. So to support and manage this infrastructure, train the students, and maintain our processes, we have a group of employees, technicians, and research professionals that are dedicated to the lab. So our team is not responding to or under a researcher per se, but under the lab's management committee, so that we answer to the lab's director and to the management committee, but researchers have no idea what kind of external services we do. So if there could potentially be some research that is very close to someone that's doing research here, there is a total disconnect between what we do as external services and what the researcher does. Furthermore, anything that's developed in our lab which is not covered by an NDA and is deemed stable and reliable enough for an external service will be used. So that can be something that was developed for the energy platform, 3D electronics. I personally don't care where it comes from as long as it's stable and not covered by an NDA. If a customer needs to have this type of process for their fabrication, I can use it. So we have a very broad material list that we can process. As long as the material is not contaminating to our machines or to our process, we are more than welcome to process it. We can process small dies up to 150 millimeter wafers. We have lithography capability, mask fabrication. We can deposit a very broad range of material, whether it be E-beam, sputtering, PCVD, plating, LPCVD. We also have a CVE system. We have dry and wet etching capabilities. We have some FIB. We can also do ion implantation and annealing. We have a CMP and a large range of characterization capabilities. And also we have access to a state-of-the-art cryogenic facility where we can do device characterization. So really we have all the building blocks required to make a JFET. So let's start with the limitations of what we can do. For this specific platform, in terms of sample size, we are limited to 100 millimeter wafers or less. For dicing purposes, we require a minimum spacing between each die of 200 microns. We also require an exclusion area of about 5 millimeters all around the outer edge of the wafer. This is really a machine limitation. Minimum feature size, 5 microns. Alignment accuracy, 2 micron. Now, all of these are highlighted in the PDK that Farouk presented to you earlier and the user guide, but I know these are usually the main hot topics that are requested. The alignment features are something that we select because we're the ones that will be doing the lithography. This is not using a stepper. This is someone's eye aligning this, so we select the alignment features. We also add test features, typical TLMs. If the customer does not want test features specifically on their die, that's fine. We need real estate to put these test features, and we also have control process windows that we put, whether it be for controlling PCVD deposition layer or etching during the process without going into the dies per se. We all these features outside the dies of the customer. Finally, for ion implantation and annealing is simulated here based on the type of oxide that we used and also based on the doping levels, species, and profile that is requested for the device that we're making. And finally, the contact annealing is chosen based on the metal used for the contacts. Now, what we are working with as a standard epi structure is an N-type silicon 100 substrate, 100 millimeters, for 125 micron thick, single side polished with a resistivity of 0.006 to 0.02 ohm centimeter. And the epi layer on top of that is an P-type silicon, boron doped and 1.6 micron thick and 3 ohm centimeter in terms of resistivity. So if someone's designing their device, this is the base material you have to work with. So given that the design may change from one designer to the next, we are very flexible in terms of the doping species level and depth that we can provide. This being said, we are limited to what our machine can do. This being said, we can also use double ionized species if the depth is not sufficient for a single ionized species. Other thing that we can change in the process is the material used for the contacts. Usually for silicon, we use aluminum and aluminum silicon. If for some reason X or Y for process compatibility after we make these, this is not a good material selection, then we can change the metal contacts. This being said, we need to make sure first that we can deposit the material in the house, and then that we know that we've actually tested in the past this metal on silicon, know for a fact that it is a good contact. And afterwards, for the annealing method, we have a rapid thermal annealing system or a furnace. So either one can be used. It really depends on the material that we're using and the conditions, the best conditions to make a good contact for this material. For the ion implantation, though, furnace annealing is absolutely required because of the high temperatures required and that the RTA just cannot achieve. So if we just look at the general fabrication process, we start with the epi wafer on which we deposit oxide, and then we etch the oxide and implant. Now, why am I etching? Sometimes we don't etch and we let the oxide there during the implantation as a stopper for the implantation. Well, we're doing that because we're doing PCVD oxide and not thermal oxide. And the reason for that is when you do thermal oxide, you're going really high in temperature and it can degrade the epi interface. We don't want that at all. We want a nice crisp NP interface, so we're avoiding those high temperatures that you usually do during your thermal oxidation. So that's why we etch the oxide, we implant, we anneal, and then we metallize. Now, since the backside gate is a full wafer contact, we just do the deposition and then do the front side metallization, anneal, and then passivate, and then open the pads and the channel. Now, when we open up the channel, I want to reassure everyone on the call, webinar, that the silicon surface is not exposed to plasma at any time. So we try to maintain the surface quality of this top silicon channel as best as possible. So again, I mean, there's flexibility here where metal is concerned, size also as well. I mean, Farouk showed us an example, typical example of what was done in the past, but we are not limited to that. So the dimensions are specified in the user guide, but they're about 1.5 by 1.5 centimeters. If smaller dies are required, then that's always possible and must be discussed with CMC. When we do make these devices, we do basic IV characterization to make sure that everything works as it should. You can actually see here a typical example of what was made in the past. The test conditions for these are not, you know, I don't take this out of a hat. I really am guided by the designer of the device, because I make these devices, but I don't design them. So I need guidance in terms of test conditions and typically what I should be getting in terms of good response or typical response for this type of device. Now we have multiple test stations that we have at our disposal. So we have typical IV that we can do. We have capacitance versus tension. We have conductance versus frequency that we can do. And we have a broad range of frequency, AC amplitude, DC polarization that we can have. We also have a test station that has really, really low current, like in the picoamps, if required. So we can use the machine that's needed to do basic electrical characterization of the device per se. We can frequency, amplitude, polarization. So really, the limitation here for basic electrical characterization is not the testing capability. I think it's more the time that we allocate for this sanity check to make sure that things are working properly, the contacts are good, before we send the device over. So if you want more information, your first point of contact should definitely be CMC Microsystems. And if you want to contact me, you can also do so at the following email address.
Thank you very much, Marie-José. So I will take back the screen share now. So I hope you've started to get a flavor of how this platform can open the door to R&D applications for a number of different soft materials. So let's consider in the next couple of slides just two kinds of applications as examples. This first example is in fact documented in the reference design. It integrated a colloidal quantum dot film onto the open gate to make an ultra-sensitive infrared light detector. In this case, the designer synthesized their own quantum dots engineered to absorb light in the range of 1300 to 1500 nanometers. And these were spin-coated on top of the chip to prepare the photoactive gate. They had to use some specific surface chemistry to ensure rectifying heterojunction between the quantum dots and the silicon. But once that was successful, then you could see on the right that the light signal produces a photovoltage which shrinks the depletion region in the silicon channel and thus increases its conductivity. This was simulated in the Centaurus device environment, first of all, and two of those simulations, including their source code, are bundled with the reference design and are available to designers as part of the design kit. And finally, on the bottom right of this slide, the spectral response of the device as measured by the designer is shown. And you can see that the photocurrent as a function of light wavelength shows both what is native to the silicon-only JFET and then what is achieved as a result of integrating quantum dots with directly onto the JFET surface. These results are published in the reference at the bottom right and also detailed in the reference design. The test fixture that was used for this application is accessible if users want to use that to experiment with their chips. A second possible application is for compact biosensing. So various binding strategies could be used here, such as hybridization, enzyme reactions, or immunosensing, as long as the system is engineered to produce a charge transfer with the JFET surface. And depending on the exact system, this could happen label-free, or it could make use of an enzyme label or some other intermediate film for charge transfer, like an organic conducting polymer, for example. Now, this particular application has not yet been demonstrated with this JFET platform, but it is the kind of use that would be interesting to investigate collaboratively in the lead user run. So next, I'll talk about the lead user run, exactly how to participate in it and what the schedule is. The URL that you see on the screen now is not live yet as of today on March 20th, but will be soon. So I would suggest, if you are ready to get your hands onto this PDK right away, email us and we can get you access to the files right away, and then follow up with an email in the near future when this product page is live. So I'll explain first of all what I mean by lead users. This technology is still somewhat experimental, and so the lead user run will be a sort of collaborative research and development endeavor. Lead users we're looking for should be willing to share feedback and know-how as you learn it, and that could take place through conference calls, the preparation of your own reference design throughout the course of the project. We expect lead users to have already an existing application in mind with a soft material on hand to be integrated with the JFET platform. Furthermore, you should be available to participate within the project timelines that will be shown on the next slide, and should be a CMC prototyping subscriber once you're at the point of confirming your spot on this run. The schedule of the lead run is shown on the left here. So following today's webinar, you can get access to the PDK and have a look at it and start experimenting with your design, aiming for an application deadline on the April 13th. Following that, when a designer's spot on the run is confirmed, we'll have some time to interact over the exact design and packaging needs. Physical samples of the reference design chips are also available to ship to designers if they want to make their own inspections or measurements on these chips. Or perhaps some of you may find those chips directly useful already to your application. May 21st is the design submission, and then following that, you see dates for tape out, delivery, and in January of next year, 2019, a test report or reference design shared with the community, which captures what you learned in your experience with this technology. I'm happy to say that the cost for lead user participation in the baseline process will be free of charge this lead run. And that's in exchange for the collaboration that we'll receive, just covered on the left. The baseline process that Marie-Josée already described to us is described there on screen. And a number of options are possible, sub-dicing to smaller die and some custom process parameters for implantation and annealing, also the possibility of custom electrical characterization. So all of these needs you can communicate to us in your application form when that time comes. I'm showing now a screenshot of the product page. This, as I mentioned, is not live yet today, but once it is, it may not appear exactly like this, but the two main links of interest are circled in green there. One you can follow to request access to the cloud instance of the design environment, and then another link to follow to actually subscribe to reserve a spot on the run. So now I'd like to move to take a few minutes to take questions from the participants online now. And we're looking for any kind of questions that may have occurred as you watch this webinar about the technical features of this technology, perhaps questions about your particular R&D application, what packaging requirements you envision, or any other questions that you may have about accessing this. Please use the text chat box in your Zoom window to submit these questions. Okay, so we have one question here that asks, any application with 2D or two-dimensional materials? So the application with 2D materials, that is certainly one of the applications envisioned in the development of this platform. So there has been no use demonstrated as yet, but this is a collaborative effort, and we're looking to you, the design community, to apply these, to explore these additional applications. The following run starts on the date shown on the screen on the left. There's an application deadline on April 13th, and then you should receive confirmation of acceptance or not within a week of that, and then a design submission scheduled on May the 21st. Okay, I see a follow-up question. Is there another run scheduled if you're not able to participate on this one in May 21st? There's not one scheduled today yet because we're still gauging demand and what kind of technical requirements are needed by the community. So if this date does not match your schedule, do still get in contact with us, and we'll probably survey for demand for a second run in the following months. Any other questions? Could I maybe survey participants on the call if you feel comfortable doing so, just giving an indication of what kind of R&D application you have envisioned. Here's another question, should I use Centaurus? So Synopsys Centaurus is one of the tools that the design kit was built to use. So yes, you can use Centaurus to run simulations using the reference design simulation files. And again, if you don't already have access to the Synopsys University bundle, you can order that product through CMC's CAD tool offerings. You'll see in the reference, so there's a follow-up question about whether Centaurus could be used with a new soft material. If I understand that question correctly, the reference design and reference simulation files have to do with this application that I'm showing on screen now, the quantum dots. The designer is expected to build their own simulation models for whatever their material is. You do not have to use Centaurus for this purpose if you already have simulations built up in using another design tool. This is just meant as informative to allow you to simulate the required doping parameters and the junction parameters that would inform what you request in your design. If you have another way to obtain the same simulation, feel free to use that. If you have any other questions, please enter them into the chat function now. Okay, I'm not seeing any further questions, so if you're interested in getting started with this or learning any other details that have not been covered in this webinar, please reach out to us at either of the contacts shown on screen now, and we'll get you started on the next steps. There's a couple upcoming events shown up just for your information. So with that, I thank you for your participation in today's webinar. Please watch for a follow-up email that will provide links to a recording of this webinar and a copy of the presentation materials. That concludes today's presentation.